talk, and my talk is devoted to proposing the study of a new class of manifolds of dimension greater or equal to 2, which comes from joint work with Ingrid Bauer and our work was motivated by the study of Inoue surfaces. So in this talk, Inoue surfaces are certain surfaces S of general type with Ks ample, K squared S equals 7, and Pg equal 0. So actually, well, these surfaces have been constructed by Inoue in 1994. So a partial disclaimer, more known are the Inoue surfaces which are not algebraic. Okay, so this is like the second Inoue surfaces. So in the 70s, Inoue constructed some non-algebraic complex surfaces, and after some, well, about 20 years afterwards, he constructed these examples, and they are important because among surfaces with geometric genus 0, this is the only known class of surfaces with k-squared 7. And our remark, so he constructed the Inoue surfaces as some surfaces contained in a product of 4 elliptic curves, but we observed that S is contained in a product of 3 curves, E1 times E2 times D. So they actually, sorry, they are not contained, there exists a surface S hat contains in E1 times E2 times D, where E1 and E2 are elliptic curves. So the genus of E1 is equal to the genus of E2. This is 1, and the genus of D is equal to 5. And S, and if S is the quotient of S hat by a group G, which is isomorphic to Z mod 2 to the 5, to the 5th power. So all this, and so the theorem, which will be explained in English lecture, the theorem says that any surface which is homotopically equivalent to an Inoue surface is an Inoue surface, and Inoue surfaces form an irreducible unirational component of the moduli space of dimension 4 generically smooth, normal, and the first homology group of S is Z modulo 4 plus Z modulo 2 to the fourth. So this is the new information, and you see that the first homology, so here get Z2 to the fourth, and then Z to the modulo 4 maps to Z modulo 2, so you see the epimorphism onto G clearly, but G is not the homology group, it's a little bit larger. Okay, so I think this is the theorem. And so we proved some similar theorem before for the surfaces introduced by John Gay in 1988. Then we proved something similar for the Brunat surfaces. Then Kaplan and Chan proved some similar result for the Kulikov surfaces. So it looked interesting to try to see whether we can, how much we can generalize this kind of results. And today I will explain how a certain part can be generalized in a quite general setting, except that at some moment the arguments become more delicate. So let me quickly review the notion of strong and weak rigidity. So the definition of Z, a projective manifold, is strongly rigid this means that any other projective manifold which is homotopically equivalent to Z then either Z prime is isomorphic to Z or Z prime is isomorphic to the complex conjugate variety. And we say that is weakly rigid the statement, the hypothesis is the same. So there exists a connected, there exists a family of deformations of Z with connected base such that Z prime or Z prime conjugate belongs to the family. So the notion of strong rigidity is known. Weakly rigid, I don't know. I think I invented this name some years ago. And well. So typical example. So example 1 is a curve of genus G, at least 2, or well, a curve. C is a curve. Is weakly rigid. So this is of course not a trivial statement, but it's known, it's just the irreducibility of the moduli space of curves of genus G. Example 2 is due to Mostow and Siu. When did I actually start?
45.
And what time is it now?
57.
Okay.
56.
Okay, so most of CO, they say that locally, an irreducible, locally symmetric manifold is strongly rigid. M is equal to D modulo gamma, where D, so where gamma is the fundamental group of M. So the universal, if the universal covering of a projective manifold is D, a bounded symmetric domain, irreducible bounded symmetric domain, then M is strongly rigid. Irreducible bounded symmetric domain, the case of the curves, you have weak rigidity, so of dimension at least 2. Then M is strongly rigid. And we shall refer to this as irreducible locally symmetric variety. So in fact, Siu proved, Siu plus Samson and Ilse, they proved that if there exists a homomorphism pi 1 of Z onto if there is a well, it proved a slightly different theorem, but from this it follows that if there exists a surjective homomorphism from the fundamental group of Z to the fundamental group of M, and Z is scalar, compact, then there exists a holomorphic map realizing this homomorphism. So this is the famous theorem of a complex analyticity of harmonic maps. So the reason of this theorem is that, so the reason behind, recall the definition that Z is a K pi 1. This means that the universal covering of Z is contractible Z tilde is contractible, and the fundamental group of Z is P. And the property that it is a K pi 1, so typical example is a torus, or Z is an abelian variety. The universal covering is C to the n, but also examples 1 and 2 are examples of K pi 1. Because, well, the universal covering is a bounded symmetric domain, and the bounded symmetric domain is contractible. And the property is that, so the remark is that if Z is a K pi 1, well, and then you have that there exists a homomorphism pi 1 of x u to pi 1 to p, which is pi 1 of z. Then there exists a continuous map which realizes u. F such that pi 1 of f is u. So whenever you have a K pi 1 and you have a homomorphism of fundamental groups of some space, then this is realized by continuous map. And in this case, Ilse and Sampson prove that this continuous map can be chosen, can be made, deformed to be made harmonic, and then CU proved that, again, I forgot as the usual assumption that the dimension should be at least 2. If the dimension is at least 2. And the reason why I realized that I forgot this is that what happens when the dimension is 1. So CO then proved some result also in the case where M has dimension 1, but the best result, there were several results, and the best results is the following, is that there exists F from a projective manifold to C where the genus of C is G, at least 2, if and only if there exists a homomorphism U from the fundamental group of X onto PG is the fundamental group of a curve of genus G with kernel of U finitely generated. And it's rather clear that if you have, there exists a surjective map. should be non-constant. I mean, okay. I try not to be sloppy, but at a certain moment, if time is going quickly. So a non-constant map, then the kernel, then so this constant, this will be surjective and with connected fibers. Okay, no. It's okay. Yeah. It should be with connected fibers. Otherwise, it could be a covering space and you don't have a surjection of fundamental group. Okay, now I think is okay. So we get that certain homomorphisms, surjective homomorphisms of fundamental groups, they are induced by holomorphic maps. So, and this was used, this result or other result were used to give other example. Example 3 are varieties isogenous to a product. If Z is the quotient of a product of curves divided by G, where G acts freely and the genus of each curve factor is at least 2, then Z is weakly rigid. And example 4, assume for simplicity, so as in example 3, and assume that G acts diagonally. So diagonally, this means that G is contained in the product of the automorphisms of each vector. And then, if Ci, the quotient map of each Ci, has quotient equal P1, and this is branched on just 3 points, and is branched on 3 points, then Z is rigid. And since this example was inspired, since this class was inspired by an example of Beauville, then we proposed to call this, we say that Z is a Beauville variety. So Beauville variety is a very simple example of a manifold which is rigid, strongly rigid. And there are simpler characterization. And the last example, using these ideas, Kochik proved well. And then last example is Z is a Kodaira surface, is a Kodaira fibered surface. This implies that Z is weakly rigid. And this result was first gotten by Jost and Yao, and then the best formulation was found by Kochik. Okay, so I think I said more than enough about this. So now we have these examples of strongly rigid varieties, and now we look at our example. So an Inoue surface, right, and I mentioned that also abelian varieties are, elliptic curves are also weakly rigid. So in our case of Inoue surfaces, we have that S is the quotient of a divisor in a product, and this product, if we call it Z, this Z is a K pi 1 and is weakly rigid. Okay, so we finally come to the proposed generalization of this construction. So, definition, we say that X is an Inoue type manifold and so we just do like in this case, if there exists a unramified cover, so an unramified cover with group G, with Galois group G, so X is equal to X hat divided by G. G is again a finite group acting freely on X hat. The quotient is X, such that X hat is an ample divisor in Z. Z is projective because it contains an ample divisor, and such that Z is a K pi 1 or K gamma 1 complex manifold. Okay, so we just mimic this and we replace the product of these three curves by any K pi 1, but for notational reason I denote by gamma the fundamental group. So the remark is that X hat, so I think in Inoue type manifold, we assume that the dimension of X is at least 2. So this notion is for surfaces but also for higher dimensional varieties. The fact that the dimension of X is at least 2 allows to use the Lefschetz theorem. And so by Lefschetz, it follows that the fundamental group of X hat is equal to the fundamental group of Z. This is gamma. And therefore, we have an exact sequence of fundamental groups. 1, gamma, the fundamental group of X, contains the normal subgroup gamma, and the quotient is the finite group G. So this is the definition. Well, the definition is a little bit too general, and however, I show that there are many examples, and so we say, moreover, we say that so X is an Inoue type manifold. If I say that if it is of special type, well, the hypothesis is of special type if, moreover, Z is a product Z1 times Z2 times Z3, where Z1 is a product of abelian varieties. Z2 is a product of curves. Curves of genus at least 2. And Z3 is a product of locally symmetric manifolds Mi. Irreducible locally symmetric. And I will say that it is classical type means that you forget about this Mi. So the situation then classical type means that Z is Z1 times Z2. There are only curves and abelian varieties. No, sorry, I'm not finished with the definition. Okay. So now I have to put some conditions in order to get some result, and I cannot explain. You will see it in during the talk on Inoue surfaces why we have to put some condition. And moreover, we assume that G, the action of G on X hat is induced by an action on Z. On Z, and we assume that this acts diagonally. This is the first property. The second property is that G acts faithfully by conjugation on gamma. So G injects in the group of outer automorphism of gamma. And now I have to explain why I write this. A product of abelian variety is an abelian variety, okay? But so why do I distinguish the factors? So in the Inoue case, you have some elements of the group which act by -1 of the first elliptic curve and trivially on the second, and conversely. So you can separate the factors. So third, we have the sure property holds so we set lambda j to be the lattice associated to the jth factor. So define lambda j to be the fundamental group of AJ. And then this is a free Z module, and you associate to this the vector space lambda j tensor Q. And then the property is that all these vector spaces are representations of G. And so they decompose into irreducible. And I want that the representations in two summands here, you never get the same representation. And so the sure property is hom Vi Vj G is 0 each time that I is different from J. Okay, so maybe let me check that these are all the properties. So usually, I mean, you add the property during the proof if you realize that it's not enough. Okay, right. Okay. Okay, so this is the definition, and now maybe in the title I said strongly rigid, weakly rigid, and then semi-rigid. So I will not explain what is semi-rigid because it's a little bit like, so it's something a little bit less than weakly rigid. So now I would like to prove that the big question is, so the question is which Inoue type manifold are weakly rigid. Well, as I started in the beginning, and I just, what I wrote here is that something homotopically equivalent to a Inoue surface is an Inoue surface, and they form an irreducible irrational component. So what I wrote here more precisely, but says that Inoue surfaces are weakly rigid. And we also have other examples which are weakly rigid. And so the first step is to show that any other manifold which is homotopically equivalent to a Inoue type manifold is again an Inoue type manifold. Okay, so step one, so first, so we prove under certain condition that X prime homotopically equivalent to X and X is an Inoue type manifold implies that also X prime is an Inoue type manifold. Okay? So this result is, I think, hopefully can be improved. At this moment, we have some partial result, and there are several hypotheses. So I will state a theorem under some assumption. So let X be a Inoue type, a special Inoue type manifold. So should be a set. And assume that the class of x prime of x hat is that the cohomology class of x hat in the cohomology of Z is indivisible. Okay, now let x prime be homotopically equivalent to x. This is the, okay, we can actually weaken the assumption but I will do it later, and assume that, well, if we want Inoue, we can also generalize to Inoue type varieties, but now I concentrate on manifolds, so these have ample canonical bundle. So this is a necessary condition. Assume that Kx prime is ample, and Kx prime to the n is equal to Kx to the n. Then x prime is also an special Inoue type manifold. And let me denote by W is the, so I hope you understand my notation. X prime, so X has a finite Galois covering X hat, and this is the étale cover we have that the fundamental group of X prime is the same as the fundamental group of X, and this surjects onto G. So they are homotopically equivalent, so the fundamental groups are the same, they have a surjection to G, and so I take the associated subgroup gamma, and so they have, there is a corresponding étale covering, and this X prime hat is contained in also in a Z prime, and then W, which is X prime hat, is contained in Z prime, and Z prime has the same form. It's a product of abelian varieties of the same dimension times curves, other curves, and a product of locally symmetric M prime, and where M prime I is Mi or Mi conjugates, and the action on each vector is the same. So for the last factor, well, it's either mi or mi conjugate. So of course, mi has an action, also mi conjugate has an action. Now for curves, so let me recall a theorem or proposition which I proved some years ago, and says the following, which is this proposition was the key result to prove weak rigidity in example 3. And the curves of genus G with an action of a finite group G what does it mean that you give an action, they correspond to the orbifold fundamental group exact sequence. You can define, you have pi G, that's a fundamental group of a curve of genus G. Then you define the orbifold fundamental group of this action, and it has a surjection onto G. And one sees that giving the topologically action is the same as giving the class of this extension, and is the same as giving the injection of G in the automorphism, the group of automorphisms of PG, which is the mapping class group in genus G. So with a given topological action, and according to a result of Nielsen, which you can also reprove in other ways, giving the topological action of a group, this is nothing else than giving the stabilizer in Teichmüller space of the corresponding point. And the proposition says the curves, so you fix this mapping, equivalently you fix this extension, they form an irreducible family. Form a connected family. So this means that the curve C prime H and the curve CH, they have an action by the group, but it's the same topological action. So for curves, it is clear because this conjugation fully represents. Now, for the abelian varieties, the action of G here gives a linear action. And this is not sufficient, so let me erase here. So for abelian varieties, for A, J, and A prime J, we get the extension one lambda J G J bar G. So this is a lemma which I wanted to prove, but I realized I will not prove the lemma. So if I get an abelian variety and then I get this orbifold exact fundamental group exact sequence, this determines uniquely the real affine type of the action. So the linear part is given by conjugation, but any group acts on an abelian variety. If you lift it to the universal covering, it gives you an affine representation. And this exact sequence uniquely. So you see that this theorem says that essentially up to weak rigidity, Z and Z prime are in the same family. And the only problem which remains is that x hat is invariant by the action of G, but the question is whether x hat and x prime hat, these coverings, these divisors can be deformed to each other. And this is the serious issue which remains open. But at least this theorem solves for us the first part, the first difficulty. So let me try to explain the ideas of the proof. Yeah. Okay, so okay, so idea of the proof. So I take x prime, which is homotopically equivalent to x. So the fundamental group, so I consider, so x prime is homotopically equivalent to x. So the fundamental group of x prime is the same as the fundamental group of x, and therefore, so contains the subgroup gamma. So let W, the covering of x prime corresponding to the subgroup gamma. So that x prime is W modulo G. And what we want to prove is that G is a divisor in a K pi 1. Okay, now we know that pi 1 of W is gamma, and gamma surjects onto the fundamental group of Mi, because gamma is just the product of all these fundamental groups. And gamma also surjects onto the fundamental group of Ci. So, by the theorem of Cu and this other theorem, these surjections by the above theorems, these surjections are represented by holomorphic maps. Okay, so by holomorphic maps from W to M prime I and from W to some other curve of the same genus. Okay? In the case of mi prime by Cu by strong rigidity is either mi or mi conjugate. In the case of the curve, you can vary. So we define Z prime 2, well, as we did, so with the prime, as Z prime 2 is the product of these curves. Z prime 3 is the product of the locally symmetric factors. And therefore, W has a mapping to Z prime 2 times Z times 3. So now to construct Z prime, now it's not difficult because for Z prime 1, we just use the Albanese map. W goes to the Albanese of W, and here you go to the Albanese of Z prime 2 times the Albanese of Z prime 3. So we get, by the universal property, we get this map. But if I take homology, first homology group of W modulo torsion, which is the fundamental group of Albanese, is just the first homology modulo torsion, and this is just splits as lambda direct sum the fundamental group of the Albanese of Z prime 2 plus the fundamental group of Albanese of Z prime 3. So I have a mapping of abelian varieties, but this induces a splitting of the lattice. So this implies that this Albanese variety is a product of this and this. And so this implies that Alb of W splits as A prime plus Albanese Z prime 2 plus Albanese of Z prime 3. So I found A prime. So we define Z prime as A prime times Z prime 2 times Z prime 3. Okay, and lambda is the fundamental group of A prime. But I know that lambda is a direct sum of this lambda j. And this lambda j, they are different representations. So the action is holomorphic, and the action is holomorphic means that multiplication by the square root of -1 commutes with the action of the group. But if an endomorphism commutes with the action of the group, it sends a representation of a certain type to a representation of the same type. But here in different summands, they're never the same representation. So property, the sure property, implies that lambda j tensor R modulo lambda j, this real torus is a complex, is invariant for complex structure. And this means that A prime is a direct sum of A prime j. So the sure property immediately implies that the splitting factor for the Albanese again splits. So I get a mapping here. So now that finally, let me, I don't know how much am I entitled, let me take 5 minutes, okay? If there are no strong objections. I mean, because I put the sure property, and then I've been talking over and over about this k pi 1 property. So the important thing is that now I have W, which is the étale covering of X prime, gets a holomorphic map to Z prime. And now, of course, I get F upper star, the pullback from the cohomology of Z to the cohomology of X hat, but this is the same, is identified to the cohomology of W. Since they are homotopically equivalent, also the associated covering are homotopically equivalent, and they have the same cohomology algebra. On the other hand, this is a k pi 1. So it's a quotient of something contractible by this group acting freely. So this element here is just the cohomology of the group. So this mapping here, F, so F star is determined by pi 1 of F, which is just the isomorphic of the fundamental group of W with the fundamental group of Z prime. And so the pullback of the, yes, Z prime and Z are the same. It follows, the conclusion is that the class, so the class of W prime, the image of W is the same as the one as the image of X hat. So in both cases, these varieties have the same class. And if this class is indivisible, it follows that F of W, let me call it W prime, is a divisor, and F is birational. Because it cannot cover the image with multiplicity. Okay, so the only thing which is left now is the final claim is that F is an embedding. Well, F, to prove that F is an embedding, we just use adjunction theory. So by adjunction, so first of all, we get W goes to W prime, but this mapping is birational, so it factors through the normalization. And now you see that the main point is that the canonical divisor of W is just the pullback of the canonical divisor of W prime minus an effective divisor. So first of all here, minus A, where A is effective, and A is the conductor divisor. When you normalize, you get this conductor ideal, and you take the associated divisor, and then here you get some divisor plus B, and B is effective because since KW is ample. So this is the only delicate point, is this lemma, which was proven, I don't know by whom first, by Matsuki or Corti, anyhow is in the book by Collar and Mori, and just says that if you, from a normal variety, you take the canonical divisor, and if this is P ample, then you just always subtract. And the conclusion is we want to use this assumption. And so the main point is that now so I have that KW plus A to the n is F upper star of KW prime to the n. But now comes the property that W prime has the same class as the image of Fx hat. And so this is just F upper star of K Z prime plus W prime to the n. But since Z prime is homotopically equivalent to Z, and W prime has the same class of this is nothing else as and this is nothing else than K of X hat to the n, and by our assumption, this is just KW to the n, because the two manifolds have the same self-intersection of the canonical divisor, and times when you go to a cover you multiply by the degree. So the final conclusion is that this is equal to this. And here's the point where I use that KW is ample. I have this is ample plus effective, and the self-intersection is the same. So KW ample, this implies that A is 0, and this implies that there is no adjunction, and this implies that F is an embedding. Okay, thank you for the attention.
57.